These glowing clouds in space are actually the final breaths of dying stars. For centuries, we saw them as simple, beautiful endings. But what if their beauty is a mask for cosmic chaos? We are about to journey through 50 strange discoveries that rewrite the story of stellar death. You will see how these nebulae defy physics, hide chemical riddles, and even forge the seeds of life itself. Why do some nebulas look like butterflies while others resemble perfect spheres? How can a place in space be colder than the emptiness between galaxies? The answers will transform how you see our universe. What is the most beautiful mystery you have ever seen in the night sky? Our story begins with a cosmic misunderstanding, a beautiful accident of history. The very name Planetary Nebula is a lie. It was coined in the 1780s by the famed astronomer William Herschel, the same man who discovered the planet Uranus. Peering through his telescope, then the most powerful in the world, he noticed these faint, glowing smudges. They appeared not as points of light like stars, but as small, fuzzy disks. To his eyes, they looked remarkably similar to the distant greenish disk of Uranus. He called them planetary nebulae, believing they were somehow related to new worlds or the formation of planets. This was a perfectly reasonable conclusion for the time, but it was fundamentally wrong. These glowing clouds have nothing to do with planets at all. They are the dying breaths of sun-like stars, vast clouds of gas expanding into space. The irony is profound. A name born from a limitation of technology locked a misconception into place for over a century, long after better telescopes revealed their true nature. Even today, this charming misnomer creates a ripple of confusion for anyone first stepping into astronomy, a ghost of a centuries-old era that reminds us how our view of the cosmos is always shaped by the lens through which we see it. Herschel's simple disks were an illusion shattered by sharper eyes. The next great surprise came when telescopes finally pierced the cosmic haze to reveal the true forms of these stellar ghosts. Many were not spheres at all, they were butterflies. One of the most stunning is NGC 6302, the Butterfly Nebula, a celestial insect with wings of gas stretching over 3 light-years. Its symmetry is both beautiful and baffling. Why would a star's final act produce such an intricate bipolar shape instead of a simple, expanding bubble? The answer lies in a hidden violence at the heart of the dying star. Instead of a gentle, outward sigh, the star unleashes powerful, collimated outflows. Imagine tightening the nozzle on a garden hose to create a sharp, high-pressure jet of water. In a similar way, something focuses the star's erupting material into 2 narrow, opposing jets that scream outward at incredible speeds. These jets act like cosmic sculpting tools, plowing into the slower-moving cloud of gas the star shed earlier. They carve vast cavities and funnel material into those magnificent wings. This discovery completely rewrote the story of stellar death. It was no longer a quiet, uniform expansion. It was a dynamic, directional explosion, a final, focused shout into the void that forever imprints the star's last struggle onto the nebula's beautiful form. But those sculpting jets are not the only high-speed enigmas hiding within the ghostly glow. Look closely at a nebula like NGC 2392, the Eskimo Nebula, and you will see something strange. Nestled within its glowing gas are small, dense knots like cosmic bullets frozen in flight. Astronomers call them FLIERs, an acronym for Fast Low Ionization Emission Regions. The name itself tells a story. They are fast, hurtling through space at speeds that can exceed 100,000 miles per hour, far faster than the nebula's main shell is expanding. They show low ionization, meaning their atoms have lost fewer electrons, suggesting they are somehow shielded from the star's intense radiation. And they are regions, localized clumps with a chemical fingerprint distinct from the surrounding gas. Their very existence is a profound puzzle. How did these dense knots form and get launched with such ferocity? one leading theory points back to the star in its final, chaotic death throes. Perhaps these are not part of the main, slow wind at all, but are the result of a brief, incredibly powerful burst of jet activity that occurred very late in the process. Imagine a firework that, after its main explosion, shoots out a final volley of bright sparks. These FLIERs could be that final, desperate volley from a dying sun, a last gasp of focused energy that punched through the expanding cloud, leaving behind these mysterious high-speed markers. Their unique composition is a fossil record of that single, violent event, a chemical signature from a moment in the star's death that we are only just beginning to decode. Yet for all their speed, these knots and jets are just symptoms of a deeper, more fundamental mystery. Why is the death of a star so rarely a solo performance? The growing consensus points to a hidden partner, a second star whose gravitational presence orchestrates the entire spectacle. A huge proportion of these beautiful nebulae, especially the most complex and asymmetrical ones, are likely born from binary star systems. Picture a cosmic dance where one star is dying. As it swells into a red giant, its outer layers become so tenuous that its companion star can begin to steal material away. This gravitational tug-of-war violently disrupts what should have been a peaceful, spherical expansion. The dying star's gas does not flow out evenly in all directions. Instead, it gets pulled and twisted into disks and funnels around the binary pair, channeling the erupting material into those magnificent bipolar outflows we see as butterfly wings or hourglass shapes. The companion star acts as a cosmic sculptor, its gravity carving and focusing the stellar wind into breathtaking works of art. This revelation transforms our understanding. These nebulae are not just the death throes of a single star, but the final, dramatic chapter in a long stellar relationship, a last waltz etched in glowing gas for all the universe to see. At the heart of this cosmic dance lies the final ember, a star transformed. The brilliant, sprawling nebula is just a fleeting shroud, a temporary monument to the tiny, impossibly hot cinder left behind. This is the central star, a white dwarf. Having shed its outer layers, it has collapsed into an object with a mass similar to our Sun, yet crushed into a sphere only about the size of Earth. The forces at work here are almost unimaginable. The gravitational collapse releases a titanic amount of energy, heating the star's remaining surface to temperatures that defy comprehension. We are not talking about the hot surface of our own Sun, which is a relatively mild 5,800 Kelvin. The central stars of planetary nebulae routinely achieve surface temperatures exceeding 100,000 Kelvin, making them some of the hottest objects we know of in the entire universe. For a brief, brilliant moment, this tiny, dense star burns with a ferocious, ultraviolet intensity, and it is this very light that illuminates the surrounding gas, causing the entire nebula to glow. Yet this is the climax of a star's life, not the beginning of a new era. This searing heat is the last fever before the long, cold night. Having no fuel left for nuclear fusion, the white dwarf has no energy source to sustain itself. It is simply a dying ember radiating its immense stored heat into the void, cooling and fading with every passing millennium. From one of the universe's hottest objects, it will steadily dim into a cold, dark, crystalline sphere of carbon and oxygen, a diamond in the dark, destined to drift through the galaxy in perpetual silence. This tiny, superheated white dwarf is the engine that lights up the entire nebula, but its light can do far more than simply illuminate. Sometimes it creates a cosmic illusion so strange it seems to defy the very nature of reality. In objects like Hubble's Variable Nebula, we witness the phenomenon of a light echo. The central star does not shine with a steady light, it flickers and flares unpredictably. When one of these sudden bursts of light races outward, it does not illuminate the entire dust cloud at once. The light first hits the dust particles closest to the star, making that region glow brightly. But the light continues traveling, and a few months or years later, that same flash finally reaches a more distant part of the nebula's shell, lighting it up in turn. From our distant vantage point, this creates the breathtaking illusion of vast, shadowy waves expanding through the nebula at impossible, superluminal speeds. We see what looks like a ripple moving faster than light itself, a phantom wave born from the staggered arrival of the original light pulsed to different layers of dust. This is not matter moving, but information, a cosmic afterimage that allows us to do something remarkable. By carefully tracking these expanding light echoes, astronomers can triangulate and map the full three-dimensional structure of the nebula. It is like watching a sonar pulse bounce through an underwater canyon, revealing depths and contours we could never see directly. This ghostly dance of light and shadow is one of the most elegant tools we have for turning a beautiful two-dimensional picture into a detailed cosmic map. That final, superheated ember is not just an artist of light, it is a master chemist. The common perception of these nebulae as simple, ethereal clouds of gas is a profound oversimplification. Deep within their glowing veils, astronomers have uncovered a chemical factory of staggering complexity. Using powerful infrared telescopes, we have peered into the hearts of these stellar ghosts and found them filled with soot. Not just simple atoms, but complex carbon-based molecules and tiny dust grains, the very same materials that, here on Earth, we would call the building blocks of life. This discovery was completely unexpected. How could such intricate molecules form in the violent, radiation-flooded environment surrounding a star hotter than 100,000 degrees? The secret lies in a delicate balancing act. The expanding shell of gas cast off by the star earlier in its death throes acts as a protective shield. It creates a cool, dense cocoon where atoms can link together, far from the destructive ultraviolet fury of the central white dwarf. In these cosmic safe zones, carbon atoms assemble into chains and rings, forming polycyclic aromatic hydrocarbons, which are essentially large, sturdy molecules that are the precursors to soot and other complex organics. This stellar soot is then violently ejected into the wider galaxy, a gritty legacy of a star's death. Every planetary nebula is a forge, seeding the interstellar medium with the raw materials for new generations of stars, planets, and perhaps one day life itself. The iron in your blood and the calcium in your bones were forged in stellar explosions, but the very carbon that defines you as a living being may have begun its journey in the cool, dark pockets of a nebula just like these. The soot and dust forged in these cosmic forges do not linger peacefully. They are caught in an explosive rush, a supersonic expansion that defies earthly intuition. The outer shells of these nebulae are not drifting lazily into space. They are screaming outward at velocities that can exceed 20 kilometers every single second. To grasp that speed, imagine an object traveling from New York City to Los Angeles in less than 3 minutes. This is not a gentle breeze, it is a continuous, unstoppable shockwave of gas and dust. This ferocious speed is the direct result of the earlier violence, the immense pressure from the central white dwarf's intense radiation, and the initial explosive force of the star's death throes. Yet this breathtaking velocity carries a profound consequence. It means the beautiful nebula we see is an ephemeral spectacle, a cosmic bloom that withers almost as quickly as it flowers. From the moment it first blossoms into visibility, a planetary nebula has a visible lifespan of only about 10,000 to 20,000 years. In the multi-billion-year life of a star, this is less than a single blink. The very forces that create its stunning glow are the same ones that seal its fate, pushing its material so far and so fast that it simply thins out, becoming too diffused to shine. The nebula vanishes, its substance melting back into the interstellar medium, leaving the cold, dark white dwarf as the only monument to its fleeting beauty. This chemical chaos is etched into one of the most beautiful nebulae of all, the Spirograph Nebula, known to astronomers as IC 418. From a distance, it appears as a delicate, symmetrical bubble, its surface etched with fine, swirling patterns that resemble the intricate lines drawn by a spirograph toy. But this serene beauty is a mask for a deeply strange and lopsided chemical reality. When scientists analyzed its light, they found a composition that defied expectations. The nebula holds a shocking overabundance of helium, the second lightest element. This was the first major clue that its parent star was no ordinary sun. Helium is normally a product of the nuclear fusion happening deep within a star's core. For it to be so plentiful in the outer layers that were cast off into space means that the dying star must have undergone a profound internal upheaval, one that dredged up vast quantities of this fused material from its heart and mixed it into its outer envelope before the final expulsion. It is as if the star's very engine was violently churned, spilling its deepest secrets out into the void for us to find, but the helium was just the beginning. The spectrum of IC418 also revealed a set of faint, mysterious emission lines that did not match any known element on Earth. For a time, these unidentifiable lines were a genuine cosmic puzzle. They pointed to the presence of something unknown, something forged in the extreme conditions of a star's death that we had not yet categorized. The mystery was so compelling that astronomers initially gave the unknown element a placeholder name, nebulium. It turned out that nebulium was not a new element at all, but a familiar one behaving in an unfamiliar way. The lines were coming from oxygen, but oxygen that had been stripped of most of its electrons and was glowing in the near-perfect vacuum of space, a state so rare on Earth we had never seen its signature until we looked into the heart of a dying star. This discovery revealed that the environments within these nebulae are not just hot, they are profoundly exotic, creating conditions for matter that push the very limits of physics. That profound chemical chaos finds its ultimate physical expression in the Boomerang Nebula, a place where stellar death creates a cold so deep it defies belief. This nebula holds the record for the coldest known natural location in the entire universe, a frigid -272 degrees Celsius. That is just one single degree above the absolute coldest temperature possible, absolute zero. It is even colder than the faint, leftover warmth from the Big Bang that permeates all of space. This unimaginable chill is not a sign of a quiet death, but of a spectacularly violent one. The nebula's rapid expansion is the key. The central star is ejecting material at a ferocious speed, losing mass at a rate several thousand times faster than our own sun loses in its solar wind. This is like a cosmic refrigerator. You feel this principle when you blow air out of your puckered lips. The fast-moving air feels cool because it is expanding rapidly. The Boomerang Nebula is doing this on a cosmic scale. Its gas is expanding so incredibly fast that it cools itself down to this record-breaking low. This tells us that the final stages of a star's life can be an intensely energetic, almost frantic process where the star does not just gently shed its skin, but violently flings it outward in a desperate rush. That incredible cold is the ghost of that final, explosive gasp, a permanent shiver left in the void. Even the coldest, fastest explosions cannot erase all structure. Within the vast, expanding shell of the Helix Nebula, one of the closest planetary nebulae to Earth, we find a field of cosmic tadpoles, thousands of them. These are the cometary knots, each one a dense, dark globule of gas and dust with a brilliant, glowing tail streaming away from the central star. They are not small either. Each knot's head is about twice the size of our entire solar system, a colossal structure that from our vantage point looks like a mere speck. Their name comes from their resemblance to comets, but they are fundamentally different. A comet's tail is blown by the solar wind. The tail of a helix knot is sculpted by the relentless, searing ultraviolet radiation from the tiny, ferociously hot white dwarf at the nebula's heart. This intense light boils material away from the side of the knot facing the star, ionizing it and causing it to glow, while the dense head casts a long, protective shadow behind it. The result is a universe filled with glowing, ethereal tadpoles, all swimming radially away from their dead stellar parent. But how did these immense structures come to be? Their origin is a subject of intense debate. One theory suggests they are the primordial building blocks of the star's lost envelope. As the red giant star shed its outer layers, its material may not have flowed out smoothly. Instead, it could have congealed into these vast, cold knots right from the start, like lumps in cosmic gravy. They would be fossil remnants of the star's final, churning days. The opposing theory argues they were born from a later chaos. As the main shell of the nebula expanded rapidly into the slower-moving material ejected earlier, a powerful instability could have rippled through the gas. Think of it like this: when a fast-moving river of air meets a slow-moving one, it creates turbulent wind shear, which can whip clouds into distinct rolling formations. In the nebula, this shear may have caused the gas to collapse under its own gravity into these isolated, dense knots. Each explanation paints a different picture of the star's death. Were the knots always there, witnessing the entire catastrophe from within? Or are they a secondary effect, a beautiful aftermath born from the violence of the expansion itself? Their very presence tells us that a star's final breath is not a simple, uniform event, but a layered and deeply textured process, leaving behind a legacy of tangled mysteries for us to unravel. Even the most stable-looking cosmic structures can play tricks on the human eye. Gaze directly at the Planetary Nebula NGC 6826 through a telescope eyepiece, and you might see nothing but a brilliant, solitary star. But shift your gaze slightly, looking just a little to the side, and a faint, ghostly halo of greenish light suddenly materializes around it. Look back directly at the star, and the nebula vanishes again. This is the blinking planetary, an object that appears to turn on and off like a cosmic light switch. The phenomenon has nothing to do with the nebula itself changing. It is a perfect storm of celestial contrast and the peculiar limitations of our own vision. The central star of NGC 6826 is exceptionally bright and hot, overwhelming the light-sensitive cone cells in the center of our retina when we stare right at it. These cones are great for color and detail in bright light, but they are terrible at detecting faint, diffuse glow. The nebula's light, however, is spread out and far dimmer. To see it, we must rely on the rod cells that dominate our peripheral vision. These rods are exquisitely sensitive to low light levels, though they see mostly in black and white. By using averted vision, looking slightly away from the target, we allow the nebula's faint photons to fall onto this more sensitive part of our eye, making the entire ghostly structure snap into view. This celestial blink is a humbling reminder that the universe we see is always filtered through the very specific and imperfect instrument of our own biology. That same biological quirk that makes one nebula blink reveals the profound asymmetry hidden within another. The Eskimo Nebula presents a face that seems almost human, a central visage surrounded by a complex fur-lined hood. This is no simple sphere. Its structure is a cosmic onion with two distinct layers, a bright, dense inner shell and a vast, filamentary outer shell that streams outward in delicate, radial tendrils. The inner region glows with the fierce light of the central star, a compact bubble of recently ejected gas, but the outer shell tells a different, older story. Those filaments are not random. They are the remnants of a much earlier, slower wind from the star's past when it was a cool, bloated red giant. The mystery is not that there are two shells, but why the outer one is so spectacularly lopsided and structured. What could possibly sculpt a gentle, outward breeze into that intricate Parker hood? One compelling theory brings back the hidden partner, a binary companion star. As the dying star shed its outer layers, a nearby companion could have gravitationally funneled the material, creating a dense disk around the pair. Later, The fast wind from the hot central star would have slammed into this disk, being channeled preferentially outward above and below the orbital plane, creating the bright inner bubble and pushing the older material into those radial filaments. It is a story of two separate winds from two different eras of the star's life, colliding and interacting under the gravitational guidance of an unseen dancer. Yet another possibility points to the star's own internal dynamo. In its death throes, the star's magnetic field could have amplified to incredible strengths, becoming the primary sculptor. This powerful magnetic field would have acted like an invisible cage, gripping the outflowing gas and channeling it along field lines, forcing it to erupt from the star's polar regions and creating the intricate, linear patterns we see in the outer halo. Whether through the gravitational tug of a companion or the invisible hand of magnetism, the Eskimo Nebula stands as a testament that a star's death is never a quiet, uniform surrender, but a structured and directed expulsion, its final form written by forces unseen. The serene gaze of the Owl Nebula hides a deep cosmic secret, a disconnect between the parent and its child. While the glowing eyes of M97 appear fixed in space, its central white dwarf is not resting peacefully at the center. Precise measurements reveal it is moving on a different path and at a different speed than the vast cloud of gas it created. The star is a runaway, drifting away from the very nebula it gave birth to. This presents a beautiful paradox. How can a star escape its own funeral shroud? Astronomers see two compelling possibilities, each a dramatic story of cosmic violence. The first theory involves a gravitational slingshot from an unseen partner. If the central star was once part of a tight binary system, the death throes that created the nebula could have also triggered a stellar explosion, flinging one star away like a stone from a catapult. The surviving white dwarf would now be recoiling through space, leaving its glowing legacy behind. The second theory paints a different picture of external resistance. Perhaps the star is moving at its original, steady pace, but the nebula itself is being slowed down. As the expanding shell plows into the thin gas and dust of the interstellar medium, it meets a subtle but constant drag, like a runner fighting a strong headwind. The nebula slows while the star, compact and unhindered, continues on its way, creating the illusion that it is running away. Whether kicked by a past cataclysm or revealed by a present-day drag, the Owl Nebula tells us that the structures we see in space are not frozen monuments, but dynamic actors in an endless celestial ballet. The romantic notion of a star transforming into a giant cosmic diamond is a story almost too beautiful to be true. This myth stems from a real scientific discovery about the ultimate fate of white dwarfs. These stellar embers, composed mostly of carbon and oxygen, do not have the mass to ignite further fusion. They are simply hot spheres of degenerate matter, radiating their immense leftover heat into space for billions of years. As they cool, a remarkable phase change begins deep within their cores. When the internal temperature drops below a certain point, around 5,000 Kelvin, the carbon atoms, under unimaginable pressure, begin to lock into a crystalline lattice structure. The white dwarf is not turning into a single, planet-sized gem, but is instead slowly freezing from the inside out, forming a vast crystal of carbon, more akin to a cosmic glacier of diamond-like material than a faceted jewel. This process is not swift. It takes longer than the current age of the universe for a white dwarf to cool enough to fully solidify. So while the core of a white dwarf will indeed become a crystalline sphere, it is a far cry from the glittering diamond planet of science fiction. The reality is a dark, cold, and immensely dense crystal ball, drifting in eternal silence, a monument to a star that once was. Magnetism provides an invisible force that sculpts the chaos of stellar death. We have long suspected that gravity and radiation shape these nebulae, but a deeper, more hidden architect is at work. Astronomers have now directly measured surprisingly powerful and highly organized magnetic fields within the glowing shells of certain planetary nebulae. These are not the weak, diffuse fields of interstellar space, but structured forces strong enough to grip the outflowing gas and dictate its final form. The presence of such fields solves a long-standing puzzle: how the violent, explosive death of a star can produce such exquisitely symmetrical shapes as butterfly wings or perfect hourglasses. Radiation and wind alone would tend to create a messy, spherical bubble, not a focused, bipolar jet. The magnetic field acts as a cosmic funnel. Picture a child squeezing a balloon filled with water. If they pinch the middle, the water jets out forcefully from both ends. In a similar way, the magnetic field lines surrounding the dying star can channel the erupting material, constricting its flow and forcing it to erupt primarily from the star's polar regions. This creates the high-speed, collimated jets that carve the nebula's iconic shape. But where does this powerful magnetism come from? One possibility is that it is a direct inheritance, a fossil field from the star's previous life. Just as our own sun has a magnetic field, the progenitor star would have possessed one too. As the star collapsed from a bloated red giant into a tiny, dense white dwarf, this magnetic field would have been concentrated and amplified, much like a skater spins faster when they pull their arms in. The star's dramatic contraction essentially rings the magnetic field lines tighter, transforming a modest stellar field into a powerful, focused force. An alternative theory suggests the field is born from the violence of the star's death itself. In its final, churning days, the star's interior becomes a maelstrom of convecting plasma and rapid rotation. This combination can act as a natural dynamo, a self-generating engine that creates a brand new, incredibly strong magnetic field from the sheer turmoil of the dying star's heart. Whether an ancient field amplified or a new one born from chaos, this invisible magnetism is the hidden hand that guides a star's final breath into a work of art. Magnetism may sculpt the final form, but some stars resist even that invisible hand with an apocalyptic fury. In the southern sky lies Eta Carinii, a stellar behemoth whose violent history offers a terrifying preview of a death beyond anything we have seen. It is not a classic planetary nebula, for its progenitor is a hypergiant star with over 100 times the mass of our Sun, yet the nebula it created shares a hauntingly familiar blueprint. In the 1840s, Eta Carinii underwent the Great Eruption, a cataclysm so immense it briefly became the second brightest star in the entire night sky, despite being 7,500 light-years away. The star did not go supernova. Instead, it suffered a colossal tantrum, violently ejecting an amount of stellar material equal to 10 times the mass of our Sun in a single, short-lived event. This expelled gas and dust did not drift away. It was flung outward at phenomenal speeds, only to collide with slower-moving material the star had shed earlier. The result is the Homunculus Nebula, a vast bipolar structure that looks like a cosmic hourglass or a pair of opposing, glowing lungs. This shape is the same fundamental architecture we see in many planetary nebulae, but created on a monstrous, terrifying scale. The homunculus is a planetary nebula in overdrive, a consequence of a stellar eruption of such force that it defies easy explanation. Was this a true supernova that the star somehow survived, a blast that ripped away its outer layers but left its core intact? Or is this a unique form of stellar death, one where the radiation pressure building within the star becomes so intense that it literally blows the star apart from the inside out, piece by piece, in a series of violent paroxysms? Eta Carinii is a ticking time bomb destined for a final, ultimate supernova explosion. Its great eruption may have been just a warning shot, a final practice run before the main event, showing us that the processes which create the beautiful nebulae around Sun-like stars can also operate with unimaginable cosmic violence in the universe's most massive and unstable suns. The violence of a hypergiant is one extreme, but even a more typical star's death can produce a truly foul cosmic odor. drifting through the constellation of Puppies is a celestial object with a distinctly unappealing nickname, the Rotten Egg Nebula. Its official designation is OH2 31.8 plus 04.2, a name that reflects its position in the sky rather than its pungent character. This nebula earned its popular name from a single, overwhelming chemical signature, an unusually high abundance of sulfur. Telescopes designed to see in specific wavelengths of light revealed that its expanding shell is rich in sulfur compounds, particularly hydrogen sulfide, the very gas that gives rotten eggs their unforgettable and unpleasant smell. If you could somehow take a whiff of this region of space, it would be overwhelmingly foul. Yet this stench is far more than a cosmic curiosity, it is a vital clue. The Rotten Egg Nebula is not a fully formed planetary nebula like the butterfly or the Eskimo. It is caught in a breathtakingly brief transitional phase, what astronomers call a protoplanetary nebula. This stage lasts for less than 1,000 years, a mere blink in astronomical time. The star at its heart has finished ejecting its outer layers, but its core has not yet heated up sufficiently to ionize the surrounding gas and make it glow on its own. Right now, the nebula shines only by reflected starlight, a faint, cold shroud waiting for the spark of ultraviolet radiation that will soon set it ablaze. The sulfur is our window into this fleeting moment. Its sheer abundance tells a story of the star's final, convulsive breaths. As the star shed its outer layers, the process must have been turbulent and deep, dredging up material from regions where sulfur was forged and plentifully mixed into the ejecta. We are essentially seeing the star's internal chemistry splashed across the sky, a pungent preview of the beautiful nebula it will soon become. That foul cosmic odor is a prelude to a far more energetic phenomenon. Deep within the young nebula NGC 7027, astronomers found something entirely unexpected, a powerful source of X-rays. This was a profound surprise because the visible light from planetary nebulae comes from relatively cool, glowing gas. X-rays are the signature of extreme violence, of matter heated to millions of degrees. The source was traced to a ferocious collision happening in real time. The central star in NGC 7027 is expelling a scorching, ionized wind at speeds approaching millions of miles per hour. This supersonic wind is like a cosmic fire hose, and it is slamming directly into the dense, slower-moving shell of gas the star ejected just a few thousand years earlier. The impact is catastrophic. When this incredibly fast wind smashes into the almost stationary wall of gas, it does not just push it, it creates a sudden, immense shock wave. Think of the sonic boom from a jet fighter, but on a stellar scale and generating heat so intense it makes the gas glow not with visible light, but with high-energy X-rays. We are witnessing the raw, real-time violence of a star's death throes the moment its final, desperate breath crashes into its own recently shed skin. This discovery completely rewrites the quiet narrative of a star's gentle expansion, revealing a brief, intensely violent phase where the nebula's heart is a seething cauldron of superheated gas, a testament to the incredible forces unleashed when a star tears itself apart. A star can bleed for 100,000 years before it finally dies. In the constellation Cetus, the Whale, the ancient red giant star Mera demonstrates this slow, relentless leakage on a galactic scale. For centuries, astronomers knew Mera as a variable star, its brightness pulsing with a steady rhythm. But then, in 2006, a space telescope designed to see in ultraviolet light revealed something far more spectacular. Mera is not just pulsing, it is racing through space, and it is leaving behind a colossal, glowing tail stretching over 13 light-years. That is a trail of stellar material longer than the distance from our Sun to its nearest stellar neighbor. This is not the structured, bipolar shape of a mature planetary nebula, but something far more primal, the raw, untailored exhaust of a dying star. It is a direct, real-time view of the mass loss that has to happen before the final, dramatic act can even begin. Within this vast streaming tail, radio telescopes have pinpointed something even more astonishing: intense sources of microwave laser emission known as water masers. These are natural lasers where water molecules, energized by the star's light, emit a focused, coherent beam of microwave radiation. Their presence confirms that Mera's tail is not just a tenuous wisp of gas. It is surprisingly rich in water vapor and complex chemistry, the very building blocks that will one day be incorporated into a future nebula. We are essentially watching the foundation being laid, the slow, steady shedding of a star's outer identity that must occur before the central engine is exposed and the beautiful final nebula can ignite. Even our most iconic cosmic rings are not what they seem. The Ring Nebula Messier 57 is a celestial landmark, a perfect smoke ring floating against the backdrop of the Lyra constellation. For generations, we saw it as the archetypal Planetary Nebula, a simple, symmetrical loop, but Hubble's sharp eyes and advanced three-dimensional modeling have shattered that illusion. The Ring Nebula is not a ring at all. We are looking directly down the barrel of a football-shaped structure, a prolate spheroid where the long axis points straight at Earth. Its apparent circular shape is a cosmic coincidence, a trick of perspective that hid its true form for centuries. Within this glowing football, the models revealed another secret, a collection of dense, dark knots of gas swarming the inner cavity. These are similar to the cometary knots in the Helix Nebula, but they are so dark and tightly packed they remain almost invisible in most photographs, lost in the glare of the brighter gas around them. They are the shadowy inhabitants of a celestial arena, their presence only confirmed by the subtle ways they blot out the nebula's inner light. This simple ring, a symbol of cosmic perfection, is in reality a deeply three-dimensional and complex object, a reminder that the universe often presents us with a facade, hiding its truest wonders just out of plain sight. The ghost of Jupiter Nebula wears its history like a set of glowing, cosmic Russian dolls. Known to astronomers as NGC 3242, this brilliant orb reveals a double shell structure when viewed through powerful telescopes. Nestled within its bright, compact inner bubble lies a fainter, more extensive outer halo, a ghostly echo of a much earlier eruption. This layered architecture tells a story of two separate, violent outbursts separated by thousands of years. The star did not die in a single, continuous event. It experienced two distinct paroxysms. The first was a slow, massive leakage during its red giant phase, casting off a vast sphere of cooler gas that drifted outward almost lazily. Then, after a long pause, the star's core convulsed again. It unleashed a second, far faster and hotter wind, which expanded rapidly and slammed into the inner edge of that older, slower-moving shell. This collision is what we now see as the nebula's sharp, bright inner wall, a luminous shock front where the star's final, frantic breath is compressing and igniting the ghost of its first. The complex, filamentary structure within the inner shell is the direct result of this turbulent interaction, a celestial traffic jam of epic proportions where two different eras of a star's death are crashing into one another, creating a luminous tombstone with two distinct dates carved into its face. The Southern Crab Nebula presents one of the most perfectly symmetrical hourglass shapes in the entire cosmos. Its twin lobes, each a glowing bubble of gas, expand outward from a pinched central waist connected by a brilliant ring of light. This is not the work of a single, solitary star, but the signature of a stellar partnership driven to a violent extreme. Astronomers classify this as a symbiotic system, a cosmic duo with a deeply unbalanced relationship. At its heart, an aging red giant and a dense white dwarf are locked in a tight, gravitational embrace. The red giant is a bloated, cool star, slowly shedding its outer layers in a steady stellar wind. Its companion, the white dwarf, is the stellar corpse left from a previous death, possessing an immense gravitational pull for its small size. This dead star actively siphons material directly from the atmosphere of its living partner. Hydrogen gas streams from the red giant, spiraling down onto the surface of the white dwarf. There, it accumulates under incredible pressure and heat until it crosses a critical threshold. The entire stolen layer of hydrogen fuel ignites in a runaway thermonuclear explosion, a nova blast that violently ejects material into space. This eruption is channeled by the orbital dynamics of the binary pair, funneled into two opposing jets that carve out the nebula's magnificent hourglass form. We are witnessing a cyclical cataclysm, a stellar theft that leads to a periodic explosion, each outburst adding another layer to this beautiful ticking time bomb. The Egg Nebula glows with a secret history written in light and shadow. Known to science as CRL 2688, this protoplanetary nebula is a star caught in the act of dying, its central heart still hidden within a thick cocoon of dust. What makes it unforgettable are the four brilliant searchlight beams piercing that dark shroud, projecting far out into space. These are not solid structures, but escape routes for the central star's intense light, beaming through naturally formed holes in the dusty envelope like cosmic lighthouse rays cutting through a thick fog. But the true revelation lies in the delicate, concentric rings surrounding the entire system. Seen in infrared light, these perfect arcs ripple outward from the central star like waves from a stone dropped in a pond. Each one is a shell of dust, a fossilized record of a specific event. They act as celestial tree rings, marking a rhythmic, repeating cycle in the star's final millennia. Every few hundred years, right up until its final dramatic ejection, the star experienced a powerful pulse. In each pulse, it would shed a new, distinct layer of material into space. This shell would then expand outward, cooling until the dust particles within it condensed, making that particular ring visible to our telescopes. The spacing between these rings is a direct clock, telling us the exact interval between these pulses of mass loss. This was not a steady, gentle breeze, but a star coughing, a periodic and violent shedding of its outer skin. The Egg Nebula's beautiful rings are therefore a seismic readout of a star's final, pre-terminal convulsions, a stunning visual timeline of its death rattles etched onto the sky. Deep within the infrared glow of many planetary nebulae, astronomers detect a set of persistent and mysterious fingerprints. These are the unidentified infrared bands, a series of subtle emission features that show up at very specific wavelengths of infrared light. They are a universal signature, appearing not just in dying star systems, but also in the vast clouds between the stars and even in other galaxies. The pattern is always the same, a clear signal that something out there is emitting this light, but for decades, what that something actually has remained one of chemistry's most stubborn cosmic puzzles. The leading suspect is a family of large, carbon-based molecules known as polycyclic aromatic hydrocarbons. Think of these as the fundamental skeletons of soot. They are not alive, but they are complex, built from rings of carbon and hydrogen atoms fused together into sturdy, flat sheets. Their structure is perfect for vibrating in just the right way to emit that exact set of infrared frequencies when warmed by starlight. It is a compelling answer, but it is not a perfect one. The precise blend of molecules that creates the bands remains elusive, like trying to identify a specific choir by its sound without being able to pick out any single voice. How do these complex molecules, which should be torn apart by the fierce ultraviolet radiation from the central star, not only survive but thrive in such a hostile environment? The solution may lie in the shadows. Dense clumps of dust and gas within the nebula could act as protective bunkers, shielding these delicate organic compounds long enough for them to form and grow. The presence of these unidentified infrared bands is a profound clue, hinting that the final act of a star's life is a surprisingly efficient factory for the very stuff that, under the right circumstances, could one day become the foundation for biology. The universe seems to be seeding the void with the potential for life, using the death of stars as its delivery system. Yet against this cosmic chaos of butterflies and hourglasses, a single, profound sphere drifts in perfect silence. Able 39 is an anomaly, a planetary nebula so perfectly round it seems almost artificial. Its shell is a uniform, glowing bubble expanding into the void with a symmetry so pure it defies the turbulent nature of stellar death. This simple sphere is one of the rarest forms a nebula can take, and its very existence tells a story of a uniquely peaceful passing. The star that created Able 39 likely lived and died alone. Without the gravitational tug of a binary companion to pull and twist its erupting gases, and without a powerful, internally generated magnetic field to channel its outflow into jets, the star was free to shed its outer layers in a single, stable, and symmetrical event. It was a final, gentle sigh, a uniform expansion in all directions that resulted in this celestial marble. This perfect form points to a star of relatively low mass, one that did not have the internal energy for a dramatic, sculpted death. Its quiet demise reveals that the most common and beautiful shapes in the cosmos, the butterflies and the rings, are actually the products of interference, of stellar partners or internal dynamos that disrupt a star's natural tendency to die as a simple, expanding sphere. Able 39 is the cosmic control experiment, showing us what happens when a star is left to its own devices, offering a glimpse of a serene, solitary end in a universe more often defined by violent partnerships. This serene sphere is a cosmic rarity, a glimpse of a peaceful stellar end, but the universe rarely grants us such tranquility. Far more often, it delivers change at a breathtaking pace, a fact proven by the youngest planetary nebula we have ever found. The Ring Nebula, catalogued as Hen 31357, is a celestial infant. When the Hubble Space Telescope first imaged it in the 1990s, it was a small, glowing blob just beginning to shine. 2 decades later, astronomers pointed Hubble at the same patch of sky again, expecting to see a familiar sight. They were stunned. The nebula had not just aged, it had transformed. Its delicate wings had changed shape, becoming more pinched and defined. More astonishingly, the entire structure had faded dramatically, like a cosmic light bulb dimming before our very eyes. We are witnessing a stellar death in fast forward, a process that normally unfolds over millennia compressed into a human lifetime. This rapid evolution is the direct result of the central star's swift cooling. That tiny, superheated engine is shutting down at an incredible rate, its furious ultraviolet output dropping sharply. With less intense radiation to excite them, the atoms in the expanding gas cloud simply stop glowing as brightly. The nebula is vanishing not because the gas is gone, but because the light that makes it visible is being turned off. We are catching this stellar ghost in the fleeting moment it transitions from a brilliant spectacle back into cold, dark interstellar material. The Stingray offers a humbling lesson, a real-time demonstration that the beautiful nebulae we admire are not permanent monuments but fleeting phantoms, here for a cosmic instant and then gone forever. Even perfect geometry can hide a spectral enigma. Among all the strangely shaped nebulae, the red rectangle stands apart, not just for its form but for the bizarre light it emits. Officially catalogued as HD 44179, this object appears as a near-perfect rectangle of glowing red gas, crossed by a dark, ladder-like structure of dust lanes that gives it the appearance of a celestial spiderweb. Its beauty is undeniable, but its true mystery lies in its spectrum, the unique fingerprint of its light. When astronomers break its glow down into its component colors, they find something that should not be there, a set of sharp, intense emission features in the deepest red part of the spectrum. This phenomenon is called extended red emission, a name that barely conveys the puzzle it represents. The light is too red and too structured to be explained by the normal processes of hot gas or simple starlight. It is a signal without an obvious source, a cosmic question mark written in a shade of crimson we do not fully understand. The key to the red rectangle's secret lies in its heart, a tightly bound binary star system. These two stars orbit each other so closely that their gravitational embrace has fundamentally shaped their surroundings. Instead of expanding into a sphere, the material shed by the dying star has been funneled into a thick, dense disk of gas and dust that swirls around the stellar pair, a cosmic whirlpool seen almost perfectly edge-on from our vantage point. It is this disk that gives the nebula its stark rectangular silhouette. The intense ultraviolet light from the hot central stars bombards the dust grains within this disk. Scientists believe this is the trigger for the strange extended red emission. One leading theory suggests the ultraviolet light energizes tiny nanodiamonds or complex carbon-based molecules within the dust. As these microscopic particles absorb the high-energy light, they re-emit it at a much longer, redder wavelength, creating that mysterious, pervasive red glow. The red rectangle is therefore more than a nebula. It is a colossal laboratory for solid-state physics playing out on a cosmic scale, where starlight interacts with dust in ways we are only beginning to comprehend, painting the void with a color we cannot yet fully explain. The Cat's Eye Nebula stares back at us with a layered complexity that reveals a star's final, rhythmic death. When the Hubble Space Telescope pierced its glowing heart, it did not find a simple, expanding bubble. Instead, it unveiled a cosmic onion, a series of at least 11 concentric rings of gas, each one a perfect shell nestled within the next. This is not the signature of a single catastrophic eruption, but of a slow, pulsating exhalation. The star at the center of this celestial eye did not die all at once. It coughed again and again in a precise and mysterious cadence. The spacing between these luminous shells tells us the exact tempo of this stellar demise. Roughly every 1,500 years, right up to its final paroxysm, the star experienced a powerful, cyclical pulse that ejected a distinct new layer of material into space. Each shell represents a separate event, a fossilized record of the star's pre-terminal convulsions. Imagine a clock whose chimes are not sound, but expanding spheres of incandescent gas, each one marking another step toward the inevitable end. This pulsed mass loss is the key to the nebula's intricate beauty, a series of separate, overlapping funerals for a single star, creating a structure of breathtaking precision that challenges our simplest notions of stellar death. The rhythmic death of a star can sometimes sound like a cosmic siren. A rare class of nebulae known as water fountains emits a powerful, narrow beam of microwave radiation, a natural laser generated by water molecules. This intense maser emission acts like a brilliant tracer, illuminating jets of material screaming away from a dying star at hundreds of kilometers per second. These objects are not the calm, mature nebulae we often see. They are caught in a breathtakingly brief and violent outburst that may last for less than 100 years. A water fountain nebula represents the exact moment a star crosses a critical threshold. It has just finished its life as a bloated red giant and has begun its final, rapid collapse into a white dwarf. This sudden gravitational collapse unleashes an immense amount of energy, which then focuses into two incredibly fast and narrow jets. Imagine a star, having shed its outer layers for millennia, suddenly finding a new and ferocious strength, firing off twin streams of material like a celestial pressure washer. The water masers shine within these high-speed outflows, their microwaves amplified by the unique conditions of shock and density. We are witnessing the ignition of a star's final engine, the sudden, focused fury that will, over the coming millennia, sculpt the beautiful bipolar shapes of a mature planetary nebula. It is a stellar birth cry for a very different kind of life, the fleeting moment a star learns how to sculpt its own ghost. Even the most beautiful nebula holds a ghost, a mass of material that seems to have vanished without a trace. When astronomers measure the total amount of glowing gas in a typical planetary nebula, they run into a profound and puzzling discrepancy. The mass we can see simply does not add up. Based on our understanding of stellar evolution, a sun-like star should shed a substantial portion of its substance in its final death throes, perhaps 20 to 80% of its entire mass. Yet the glowing, ionized gas we observe in the nebula itself often accounts for only a tiny fraction of that, sometimes as little as 1/10 of what was predicted. So where did the rest of the star go? This is the missing mass problem, a cosmic case of unaccounted for material that challenges our entire narrative of stellar death. The first and most likely suspect is a vast reservoir of invisible gas. Our telescopes see the nebula by the light it emits, but that only reveals the gas that has been heated and ionized by the central star's intense ultraviolet radiation. Surrounding this brilliant core could be a much larger, cooler halo of neutral hydrogen gas. These atoms have not lost their electrons, so they do not glow in the same way. They are dark, silent, and incredibly difficult to detect, like an invisible ocean surrounding a luminous island. Another candidate is molecular hydrogen, where pairs of hydrogen atoms are bound together. This form of hydrogen is even more elusive, radiating its energy in very specific, faint infrared wavelengths that can be easily missed. But perhaps the most intriguing solution points to the star's own history. The final, fast wind that creates the nebula's visible structure might be just the last chapter of a much longer story of mass loss. Long before its dramatic finale, during its long red giant phase, the star could have shed a much larger, slower moving wind. This ancient material, ejected tens of thousands of years earlier, would have had ample time to drift far away, expanding and dispersing into the thin interstellar medium until it became too tenuous for our instruments to ever find. We are left with a ghost of a ghost, a stellar identity that has mostly evaporated back into the galaxy, leaving behind only its brightest, most recent shroud as a final, glowing signature. This missing mass finds its voice in a brief, almost ghostly stage of stellar evolution. Before a star becomes a brilliant, glowing planetary nebula, it passes through a fleeting transitional phase, a cosmic limbo known as the preplanetary nebula. The star's dramatic mass loss has just ceased. Its outer layers now form a vast, expanding shroud of gas and dust, but the stellar core hidden within has not yet become hot enough to flood this cloud with the ionizing ultraviolet radiation that will make it shine on its own. For now, the nebula is dark and cold, visible only because its central star acts like a flashlight, illuminating the dust from within. The Westbrook Nebula is a perfect example of this brief celestial adolescence. To our optical telescopes, it is largely invisible, a secret held in the dark, but when we point an infrared telescope in its direction, it blazes into view. Infrared light is the signature of warmth, and the dust in this nebula, heated gently by the hidden star, glows brightly in these wavelengths. This is how we catch these stellar ghosts in the act, by searching for their heat rather than their light. This phase is incredibly short, lasting perhaps only a few hundred years. It is the quiet, dark breath a star takes between the final, violent cough of mass loss and the brilliant ignition of its funeral pyre, a momentary pause before the final, beautiful flash. Even the shape of a stellar ghost depends on its cosmic neighborhood. A strange galactic pattern has emerged, a distribution that seems to defy random chance. Planetary nebulae do not look the same everywhere in our Milky Way. Those that form in the crowded central bulge, the galaxy's dense, ancient core, overwhelmingly tend to be simple, spherical shells. Yet, when we look out into the thinner, swirling disk of the galaxy where our own sun resides, the nebulae are far more likely to wear the spectacular costumes of butterflies and hourglasses. This is not a minor trend, it is a striking rule of celestial architecture. Why would the same physical process of stellar death produce such different art based solely on location? The answer seems to lie in the very different lives of the stars in these two galactic zones. The galactic bulge is a retirement home for ancient stars. These stars formed billions of years ago when the universe was much younger and possessed far fewer heavy elements, what astronomers call low metallicity. They are population 2 stars, old, solitary, and metal-poor. A star born with less heavy elements in its composition may have a quieter, less dramatic death. Without the complex chemistry that can help drive strong magnetic fields or powerful mass loss, its final breath is more likely to be a uniform, spherical sigh. It lives and dies alone, resulting in a simple, glowing orb like Abel 39. The galactic disk, by contrast, is a vibrant stellar metropolis. This is where younger, population 1 stars like our Sun are found, stars rich in the heavy elements forged in countless generations of supernova. This higher metallicity might be a crucial ingredient for a sculpted death. The extra elements could make the star's outer layers more opaque, allowing radiation pressure to build more effectively, or they could facilitate the development of a stronger magnetic field. But the most compelling difference may be social. The disk is a place where binary star systems are thought to be far more common. If a beautiful bipolar nebula is the signature of a stellar dance, then the crowded dance floor of the galactic disk is where you're most likely to find partners. The central bulge, with its ancient, isolated stars, has far fewer couples. Its stellar deaths are therefore mostly solo performances, resulting in the quiet, spherical forms that dominate its crowded skies. This galactic distribution is a profound clue, telling us that a nebula's final form is not just about how a star dies, but is deeply written into the story of how it lived, where it lived, and who it lived with. This pristine sphere of light, known as the Lemon Slice Nebula, floats in space with an almost unnatural perfection. IC 3568 is one of the smoothest and most featureless nebulae ever discovered. A luminous marble so uniform it seems to defy the chaotic nature of its own creation. Its surface is a flawless, creamy yellow glow, utterly devoid of the knots, jets, or intricate filaments that define so many of its celestial cousins. This simplicity is not a sign of a boring death, but a profound clue to a uniquely peaceful stellar ending. The star that birthed the lemon slice appears to have been a solitary wanderer, free from the gravitational tug of a binary companion that would have twisted its final breath into complex shapes. It also likely possessed a relatively calm and stable interior, without the powerful magnetic dynamo needed to channel its outflow into focused jets. Its death was a final, gentle, and perfectly symmetrical sigh, a uniform expansion into the void that resulted in this celestial masterpiece of minimalism. In a cosmos filled with violent stellar partnerships and magnetic turmoil, the Lemon Slice Nebula stands as a quiet monument to the serene death of a star left entirely to its own devices, a perfect sphere born from a final moment of undisturbed calm. That serene, minimalist sphere of the Lemon Slice Nebula glows for one reason alone, a process so fundamental it defines every planetary nebula we see. The secret is photoionization, the cosmic engine that transforms an invisible cloud of cold gas into a brilliant, colorful beacon. It all begins with the central white dwarf, a stellar ember burning at over 100,000 degrees. This star does not shine with gentle, yellow light like our Sun. It is a furious source of ultraviolet radiation, a form of light so energetic it carries the power to tear matter apart. When these powerful ultraviolet photons stream outward, they slam into the atoms in the surrounding gas cloud, the star's own cast-off outer layers. The collision is violent. The photon's energy is so great it knocks an electron clean off its parent atom. This act of stripping away an electron is what scientists call ionization. The atom, now missing a negatively charged particle, becomes a positively charged ion, adrift in a sea of freed electrons, but this chaotic state is only temporary. The freed electron, now buzzing with excess energy, cannot wander forever. Sooner or later, it is drawn back toward one of the positively charged ions. When it finally recombines, settling back into a stable orbit, it must shed the extra energy it acquired during the ionization. It releases this energy by emitting a new photon of light, but this time the light is different. It is no longer the destructive ultraviolet of the central star. It is a gentler, visible photon, a particle of light with a specific color. The exact color depends entirely on the type of atom involved and the specific orbit the electron falls into. Oxygen atoms produce beautiful greenish-blue glows. Hydrogen, the most common element in the universe, emits a deep, characteristic red. Nitrogen contributes shades of crimson. This entire cycle, from destruction to rebirth, happens trillions upon trillions of times every second across the vast expanse of the nebula. The glorious, glowing cloud we admire is not a simple reflection of starlight. It is the collective sigh of countless atoms, each one momentarily shattered and then made whole again, painting the void with the light of their reassembly. The Saturn Nebula presents a face of cosmic symmetry, its oval glow flanked by two faint, mysterious extensions that curve outward like the handles of an antique vase. Early astronomers named these features ansi, from the Latin word for handles, but they also saw a striking resemblance to the rings of Saturn seen nearly edge-on. These are not solid structures or rings of debris, however. They are ghostly bubbles of extremely low-density gas, each one a faint echo of the nebula's violent birth. The ansi mark the endpoints of the nebula's primary axis of symmetry, the polar regions where the star's final energy focused its greatest power. Think of them as the exhaust ports for a colossal stellar engine. The central white dwarf, in its death throes, did not expel its material evenly. Instead, it channeled a tremendous amount of energy into two opposing, high-speed jets that shot out along its rotation axis. These jets, moving far faster than the main shell of the nebula, raced ahead and plowed into the slower-moving gas that the star had shed earlier. The jets did not simply punch through this material, they inflated it. Like a welder using a torch to blow two perfect bubbles in a sheet of molten glass, the jets created vast, tenuous cavities on either side of the central nebula. The visible ansi we see today are just the bright rims of these colossal bubbles, the shock fronts where that ancient, fast-moving material finally slowed and began to glow. They are the lasting imprint of a star's final, focused shout, a directional fury that forever marked its tomb with the ghostly shape of a planet it never knew. The faint outer halo of the little ghost nebula holds the memory of its ancient self. This delicate, expansive shroud, far larger than the nebula's bright central ring, is a ghost of a ghost. It is the preserved remnant of the star's long, quiet life as a red giant, a phase that lasted for billions of years before its final, dramatic death. During this immense span of time, the star did not simply wait. It bled mass steadily into space through a slow, dense stellar wind, a gentle but persistent leakage of its own atmosphere. This material drifted outward for eons, cooling and dispersing into a vast, invisible sphere. Then, in a geological instant, the star's core convulsed. It shed its remaining outer layers in the fast, hot wind that created the brilliant blue and green ring we see today. When that fast wind slammed into the much slower, ancient wind, it lit up the collision zone, illuminating the inner nebula. But the older, outermost material was too distant and tenuous to be set aglow. It remained a dark, silent halo, a fossilized record of the star's patient billion-year exhalation, until our most sensitive telescopes finally learned how to see it. This faint halo is more than just an accessory. It is the foundational chapter of the star's biography, a celestial parchment that tells the story of its long, stable life before the final, beautiful catastrophe. The faintest ghosts are the ones that hold the oldest secrets. Drifting through the constellation of Gemini, the Medusa Nebula is a celestial specter so vast and tenuous it was almost lost to the void. Known to astronomers as Able 21, this nebula spans over 4 light-years, a colossal, glowing veil that marks one of the final stages of a planetary nebula's existence. It is not a brilliant, compact jewel like the Cat's Eye or the Ring Nebula. It is ancient, having spent tens of thousands of years expanding and fading. Its gases have thinned to an almost imperceptible wisp, their glow so faint that detecting them is one of the greatest challenges in modern astronomy. We can only see it at all by using special filters that isolate the specific greenish light emitted by doubly ionized oxygen, a final, faint whisper from atoms that were once part of a star's fiery heart. This immense size and profound faintness are not signs of weakness but of great age. The Medusa is a stellar ghost in its final act, beginning to dissipate and merge back into the interstellar medium from which it came. Its delicate filaments are slowly unraveling, their chemical identity dissolving into the raw material of the galaxy. Studying these fading giants is like reading the last page of a star's biography. They teach us that the beautiful, brilliant phase we admire so much is just a brief, fiery chapter. The true end is a quiet, patient dispersal, a return to the cosmic reservoir that will one day fuel the birth of new stars and planets. The Medusa Nebula shows us that even in death, a star gives everything back, its final breath becoming the first ingredient for a future universe. Our eyes see only a fraction of the cosmic story, a truth made stunningly clear by the Spitzer Space Telescope. While optical telescopes showed us glowing clouds of ionized gas, Spitzer's infrared eyes pierced the veils of dust to reveal an entirely different reality. It saw the cold, dark components of planetary nebulae that were completely invisible to Hubble and other observatories. The key is that cool dust and dense molecular gas do not glow in the visible light our eyes can detect. Instead, they radiate their energy in the form of heat at longer, infrared wavelengths. Spitzer was designed to feel this cosmic warmth, turning the ghostly outlines we knew into vibrant, three-dimensional structures brimming with hidden activity. It was like switching from a flashlight to a thermal camera in a dark room, suddenly exposing a world of life we never knew was there. One of its most profound revelations was the detailed mapping of molecular hydrogen. This is the most basic molecule in the universe, 2 hydrogen atoms bound together, and it forms in the cool, dense, and protected pockets of a nebula, far from the central star's destructive ultraviolet glare. Spitzer could see this molecular gas, tracing vast reservoirs of it that outline the nebula's true, full extent, often far larger than the glowing ionized shell. This was the missing skeletal structure, the cold bones of the stellar ghost that gave it mass and form long before it ever began to shine. Without this infrared vision, we were only seeing the neon sign while Spitzer showed us the entire building. A perfect circle of cosmic diamonds floats in the void, a celestial necklace strung with glowing beads of gas. This is the Necklace Nebula, a structure so geometrically perfect it seems designed by a master jeweler. Each brilliant bead is a dense knot of stellar material, and together they form a ring over 12 trillion miles wide. The secret to this perfect symmetry was revealed not in the glowing gems themselves, but in the tiny, frantic dance at its very center. Astronomers discovered that the nebula's heart is not one star, but 2. This close binary pair orbits each other with a breathtaking speed, completing a full rotation in just over a single Earth day. Their intimate, whirling embrace is the key to the nebula's stunning shape. Here is how the cosmic jewelry was forged. Billions of years ago, one star expanded into its red giant phase, swelling so large that its outer atmosphere engulfed its smaller companion. The smaller star, however, did not disappear. It began orbiting inside its partner's tenuous outer layers, acting like a spinning blender that churned the gas and whipped it into a vast spinning disk. When the primary star could no longer hold on, it ejected this entire disk of material in a single, titanic burst. The disk, already set into rapid rotation by the binary dance, expanded outward, and its inherent instability caused it to fragment. The same force that forms a single, continuous Saturnian ring instead created these individual, glowing clumps, each one a fossilized piece of that ancient stellar disk. The Necklace Nebula is therefore not just a beautiful accident, it is the direct and predictable result of a stellar partnership pushed to its absolute limit, a final gift from one star to another, crystallized in fire and light for all eternity. Even the most beautiful nebula is a chemical mosaic, not a uniform blend. When we analyze the light from different parts of a single planetary nebula, we find that elements are not spread evenly. Oxygen might be concentrated in bright filaments, while nitrogen pools in darker regions, and helium forms strange, isolated knots. This patchwork of chemistry, these chemical inhomogeneities, tells us the star's death was a messy, chaotic, and deeply layered event. It was not a single, smooth expulsion of a well-mixed atmosphere. Instead, the ejection process must have been lumpy and episodic, dredging up material from different depths of the star at different times. Imagine a volcanic eruption that does not just spew a uniform lava flow, but instead coughs up distinct chunks of the Earth's mantle, crust, and core, all landing in separate piles. That is what we are seeing in these nebulae. A knot rich in carbon tells us that material from the star's deep interior, where nuclear fusion forged heavy elements, was violently brought to the surface and ejected in a distinct clump. A region flush with nitrogen points to a different layer, one where the star's internal chemistry was altered by slower burning processes. These are not just random splatters, they are a forensic map of the star's final internal upheaval. But the story does not end with the ejection. Once this chemically diverse material is out in space, a new chapter of chemistry begins. Within the expanding cloud, atoms that were once neighbors inside the star now find themselves in a cold, dark vacuum. They begin to link together, forming molecules and condensing onto microscopic dust grains. An area rich in carbon and hydrogen might become a factory for complex organic molecules, while a region with silicon and oxygen might seed the growth of silicate dust, the basic ingredient of sand and rock. The final distribution of elements we see is a fossilized record of both the star's violent death and the complex chemical reactions that occurred in its expanding ghost. This chemical chaos proves that a star's final breath is anything but a simple, uniform sigh. Some of these stellar ghosts defy all expectations of scale, dwarfing their celestial cousins in a breathtaking display of cosmic excess. These are the giant planetary nebulae, vast structures that can stretch for dozens of light years, so immense they could easily engulf the entire space between our Sun and its nearest stellar neighbors. A typical nebula like the Ring spans less than a single light year, but these colossal giants operate on an entirely different level. Their existence points to a progenitor star of a very special and rare kind, a true cosmic heavyweight teetering on the very edge of destruction. The most likely creators are super-asymptotic giant branch stars, often called super-AGB stars. These are not your average Sun-like stars. They are massive beasts, born with several times the mass of our own Sun, perhaps as much as 8 solar masses. This places them squarely on the razor's edge of stellar fate. A star with just a little more mass would cross a critical threshold and end its life in a cataclysmic supernova, scattering its enriched guts across the galaxy in a final, violent blaze. But these super-AGB stars walk the line, possessing just enough mass to ignite a series of furious nuclear reactions in their cores, yet not quite enough to complete the final step that leads to a core collapse supernova. Their immense mass dictates a dramatic and profligate life. They burn through their nuclear fuel at a ferocious rate, living fast and dying young. In their final millennia, they become factories of mass loss, shedding their outer envelopes in powerful, convulsive pulses on a scale that makes the death of a star like our Sun look modest by comparison. They do not gently shed their skin, they violently eject a significant portion of their entire being into space, creating the raw material for these supersized nebulae. The giant Planetary Nebula is therefore the last testament of a star that almost went supernova, a titanic ghost born from a stellar life lived on the very brink of cosmic catastrophe. This silent symphony of light holds a secret melody, a composition written not in sound but in color. Astronomers do not just look at these nebulae, they listen to them, tuning into the subtle harmonies and dissonances within their glow. The instrument for this cosmic audition is the spectrograph, a device that splits a nebula's light into a full rainbow of its constituent colors. The result is not a smooth, continuous band, but a spectrum crisscrossed by bright and dark lines at very specific wavelengths. Each of these spectral lines is a unique fingerprint, an unchangeable signature broadcast by a particular chemical element. Intense red lines often signal the presence of hydrogen, the universe's most basic building block. A set of lines in the green and blue part of the spectrum points unequivocally to oxygen. Nitrogen, helium, neon, and sulfur all add their own distinct notes to this chemical chorus. By reading these lines, scientists can take a nebula's inventory from thousands of light-years away, determining its exact chemical makeup as precisely as if they had a sample in a lab. But the music of these spectral lines reveals far more than just ingredients. The lines themselves can be subtly shifted from their expected positions. If a nebula is expanding towards us, its light waves are compressed, shifting the entire spectral fingerprint slightly towards the blue end of the spectrum. If a section is moving away, the light is stretched, shifting the lines toward the red. This is the Doppler effect, the same principle that makes a siren's pitch drop as a police car races past you. By meticulously measuring the Doppler shift of spectral lines from different parts of a nebula, astronomers can map its complex three-dimensional motions. The sides of a spherical nebula, for instance, will show almost no shift as they are moving across our line of sight. But the front of the shell coming toward us glows with a distinct blue shift, while the back, racing away, is tinted red. This technique transforms a beautiful, static image into a dynamic movie, allowing us to see the entire structure inflating in real time, to measure its expansion velocity with precision, and to understand its true shape in the depths of space. The ghostly glow of a planetary nebula is not just a picture, it is a vibrant and moving song of its own violent birth. This breathtaking symmetry reaches its ultimate expression in the engraved Hourglass Nebula. Known to astronomers as Mycen 18, this celestial object presents a shape of such geometric perfection it seems almost engineered. Its two luminous lobes form a perfect hourglass, connected by a brilliantly defined, pinched waist that looks as though a cosmic hand has tightly cinched the nebula in its middle. This is not a gentle taper, but a sharp, dramatic constriction, and it is surrounded by a series of intricate, concentric rings that ripple outward from the central star system. This near-flawless symmetry presents a profound challenge to our models of stellar death. A simple, spherical explosion could never produce such a clean, focused shape. The secret to this cosmic corset appears to be a dense, equatorial disk of material. Picture a dying star shrouded not by a uniform cloud, but by a thick, spinning belt of gas and dust concentrated around its middle. When the star finally erupts, this dense belt acts as a powerful barrier. The fast wind from the star's core cannot easily expand outward through this heavy equatorial disk. Instead, it finds the path of least resistance, bursting forth with immense force above and below the disk's plane. The equatorial material constricts the outflow, forcing it into two opposing jets that inflate the magnificent lobes of the hourglass, while the dense waist itself remains dark and narrow, a permanent shadow of the obstacle that shaped the entire explosion. The intricate rings surrounding the structure add another layer of mystery, suggesting the star's mass loss was not a single event, but a series of precise, periodic pulses that created these luminous echoes. The engraved Hourglass Nebula stands as a stunning testament to the power of unseen structures, where a simple disk of dust can sculpt a star's final cry into one of the most perfectly defined forms in the entire cosmos. The Twin Jet Nebula paints a perfect S in the void, a celestial signature written in light. This nebula, known to astronomers as M29, showcases two spectacular jets that curve away from its central star in a graceful, symmetrical spiral. These are not gentle flows of gas, they are supersonic torrents screaming into space at speeds exceeding 200 miles per second. To travel from Earth to the Moon at that velocity would take barely half an hour. This breathtaking speed and the jet's sinuous shape make M29 a unique laboratory for understanding one of the universe's most powerful phenomena, astrophysical jets. The secret to this cosmic whirlpool lies in the frantic dance at the nebula's heart. The central star is not alone, it is locked in a tight orbital embrace with a companion, likely a white dwarf. As the primary star died, swelling into a red giant, its outer layers spilled over onto its smaller partner. This inflowing gas could not fall directly onto the dense companion star. Instead, it spiraled down, forming a vast, flat whirlpool of superheated material called an accretion disk. This disk is the engine of the jets. Friction and magnetic fields within this spinning maelstrom act like a cosmic particle accelerator, funneling some of the incoming gas into two incredibly narrow and powerful beams that erupt from the disk's poles. We are essentially seeing the exhaust from a stellar turbine, but why the elegant S-shape? The entire system is spinning. The central binary pair is whirling around, and as they move, the direction of the jet's launch point slowly precesses or wobbles, much like a spinning top beginning to slow down. This wobble causes the high-speed jets to trace out a corkscrew pattern in space. From our distant vantage point, that spiral is projected as the beautiful, shimmering S we observe. The Twin Jet Nebula is therefore more than a beautiful ghost, it is a dynamic clock, its curved jets recording the precise rhythm and tilt of a stellar dance that began millennia ago. That brilliant, sculpted ghost is a fleeting spectacle in the long life of a galaxy. The forces that create its glow are the very same ones ensuring its eventual disappearance. For tens of thousands of years, the nebula continues its relentless expansion, its outer edges screaming into the void at tens of kilometers every second. There is nothing in the emptiness of space to stop it, no cosmic wall to halt its progress. As it grows, its beautiful form begins to change. The intricate filaments stretch and pull apart, the sharp boundaries between shells and lobes blurring into a formless, ever-thinning haze. The gas, once packed densely enough to shine with fierce color, becomes more and more diffuse. The atoms within it spread farther and farther apart until the space between them is immense. At the same time, the engine of its light is failing. The central white dwarf, a brilliant ember, is steadily cooling. Its furious output of ultraviolet radiation, the very power that ionizes the gas and makes it glow, dwindles with every passing millennium. The nebula suffers a double fading, its material thinning out while the light source that illuminates it slowly dims. Eventually, the atoms are so spread out that even if a photon from the dying star did hit one, the glow would be too faint, too isolated for any telescope to ever detect. The nebula simply vanishes from view, its magnificent colors extinguished, leaving behind only the cold, dark white dwarf drifting in silence. But the story does not end there. The nebula's material does not cease to exist. Its atoms, now cold, dark, and neutral, continue their journey, mixing slowly and irrevocably with the thin gas and dust of the interstellar medium. This is the ultimate recycling. The star, in its death, has enriched this cosmic reservoir. It has salted the void with carbon, nitrogen, and oxygen, elements forged in its heart and dredged up during its final convulsions. These are the very elements that were once mere hydrogen and helium, transformed by stellar alchemy. This enriched cloud of former stardust will drift for millions of years until a gravitational disturbance, perhaps the shock wave from a distant supernova, causes it to collapse. In that collapse, a new generation of stars and planets will begin to form. The iron for a future planet's core, the silicon for its rocks, the oxygen for its oceans, and the carbon for any potential biology, all might once have been part of a beautiful, long-vanished planetary nebula. The ghost gives its body back to the galaxy, its final act a silent, generous gift to a future it will never see. A nebula's final dispersal is not the end of its story for us. The hunt for these celestial ghosts is a living, breathing field of science, one that relies as much on the sharp eyes of amateurs as on the power of giant telescopes. Professional surveys with names like MASH for the Macquarie AO Strasbourg H Alpha Planetary Nebula project have systematically scanned the sky to uncover hundreds of previously unknown objects. These are not just additions to a list, they are vital new pieces in our cosmic puzzle, each one a new laboratory for testing our theories about stellar death. Yet these massive projects often work hand in hand with a global network of dedicated amateur astronomers. An enthusiast with a modest backyard telescope and a specialized filter can sometimes spot a faint greenish smudge that no catalog has ever recorded. This collaboration between professional and amateur is a powerful force, dramatically expanding our senses of these ephemeral objects and reminding us that the map of our own galaxy is still being drawn, one discovery at a time. Why does this matter? Every new nebula found is a fresh data point. It might be an extreme example that challenges our models of stellar mass, or a strangely shaped object that reveals a new type of binary interaction. This vibrant, ongoing search proves that the story of planetary nebulae is far from a closed book, but a narrative we are actively writing together under the same night sky. The serene beauty of a nebula often begins with a cataclysm deep within the star's heart. This final, violent push is known as the helium flash, a runaway thermonuclear explosion that marks the star's last, desperate attempt to save itself from collapse. For millions of years, the aging star has been burning hydrogen in a shell around its core. The leftover helium from this process, an inert ash, has been accumulating at the center, crushed under its own weight into an incredibly dense, degenerate state. This degenerate helium core is unlike the fiery plasma of a normal star. It behaves more like a solid, its particles packed so tightly they resist further compression with a bizarre quantum mechanical pressure. As the core grows hotter and denser, it approaches a critical temperature of around 100 million Kelvin. At this precise instant, the sleeping giant awakens. The helium nuclei, which have been passively building up, suddenly and violently ignite. This is not a controlled fusion like the steady burning in the sun. It is a flash, a frantic, runaway fusion reaction that rips through the entire degenerate core in a matter of seconds. The energy released is staggering, equivalent to the entire output of our galaxy for a brief, brilliant moment. This colossal burst of energy does not cause the star to explode. Instead, it does something just as profound. It lifts the quantum degeneracy, causing the core to expand and become a normal hot plasma. This sudden expansion in the star's heart sends a powerful shockwave rippling outward through the overlying layers. It is this shock, this final seismic jolt from the core, that may provide the critical force needed to violently unbind the star's vast, tenuous outer envelope. The entire bloated atmosphere of the red giant, already loosely held by gravity, is given a decisive shove, launching it into space to begin its journey as the raw material for a future nebula. The helium flash is the star's last internal shout, a final, convulsive heartbeat that echoes through the cosmos as the first breath of a celestial ghost. Even the faintest stellar ghosts can become brilliant cosmic mile markers. Across the vast intergalactic voids, where measuring distance is one of astronomy's greatest challenges, planetary nebulae provide a surprisingly reliable ruler. This method is known as the Planetary Nebula luminosity function, and it hinges on a beautifully simple observation. Within any given galaxy, the population of planetary nebulae follows a predictable pattern. While most are faint, there is always a small group that shines with an incredibly consistent maximum brightness. It is as if nature has placed a universal cap on how luminous the brightest of these stellar ghosts can become. This brightest cutoff point becomes a standard candle, a known brightness against which we can measure cosmic distances. The principle works much like estimating the distance to a car on a dark road. If you know the true wattage of a standard headlight, you can calculate how far away the car is based on how dim its lights appear to you. In the same way, by assuming the brightest planetary nebulae in a distant galaxy have the same intrinsic luminosity as the brightest ones in a nearby galaxy, astronomers can measure their apparent faintness and calculate the distance to their host galaxy with remarkable precision. This technique has been used to measure the distances to galaxies tens of millions of light-years away, providing a crucial, independent check on other methods and helping to refine our understanding of the expansion rate of the universe itself. It is a profound thought that the final, fleeting breath of a dying star, a process that lasts for less than a cosmic blink, can become a fixed point of light by which we map the largest structures in the cosmos. These 50 strange discoveries converge on a single, breathtaking truth. Every planetary nebula is a vital link in the great chain of cosmic life and death. They are the universe's ultimate recycling centers, turning stellar corpses into the seeds of new worlds. The story begins with the pristine hydrogen and helium forged in the Big Bang, the universe's only ingredients for millions of years. Inside generations of stars, gravity provided the immense pressure and heat needed to cook these simple elements into something new. In the core of a star like our Sun, hydrogen fuses into helium. In its final, more violent stages, that helium is forged into carbon and oxygen. This is stellar alchemy, the process that creates the very elements that make our world and us possible. But these newly forged elements would be forever trapped inside the dead white dwarf if not for the nebula itself. The star's death throes are the delivery mechanism. The violent expulsion of its outer layers blasts this enriched material, carbon for life, oxygen for water, nitrogen for air, back into the galactic void. The iron in your blood and the calcium in your bones were forged in more violent supernova explosions. But the carbon that defines you as a living being was likely forged in a sun-like star and distributed by a planetary nebula. This means we are not merely inhabitants of the universe, we are its direct descendants, made from the recycled remains of stars that died billions of years ago. The beautiful, fleeting ghost we see in a telescope is not just an end. It is a promise, a generous donation to a future it will never see, ensuring that the death of one star becomes the potential for countless new beginnings. Our journey through 50 strange discoveries reveals a universe far from serene. We began with a beautiful lie, the name Planetary Nebula itself, a centuries-old misstep that masked the violent truth of stellar death. We witnessed stars that die not as gentle spheres, but as butterflies and hourglasses, their forms sculpted by hidden partners and invisible magnetic fields. We felt the chill of the Boomerang Nebula, the coldest place in the known cosmos, and saw the phantom waves of light echoes racing through cosmic dust. We learned that these glowing clouds are chemical forges, seeding the galaxy with the soot and organic molecules that are the very building blocks of new worlds and perhaps life itself. The story of a planetary nebula is not one of quiet endings. It is a dynamic, chaotic, and breathtakingly brief explosion of complexity, a star's final performance that enriches the entire galaxy. This beautiful chaos is not a sideshow, it is fundamental to the cosmic ecosystem. Every element vital to our existence, the oxygen we breathe and the carbon in our bodies, was forged in stellar hearts and delivered into the void by these spectacular stellar ghosts. They are the great recyclers of the Milky Way, turning the ashes of dead stars into the raw material for future suns, planets, and possibilities. So the next time you gaze up at the night sky, remember that the darkness between the stars is not empty. It is a vibrant graveyard and a nursery filled with the beautiful, fading ghosts of suns that gave their substance so that new stories could one day begin. What cosmic mystery captures your imagination when you look up? Share your favorite celestial wonder in the comments below. The future of these stellar ghosts is brighter than ever, illuminated by a new generation of eyes in the sky. Our journey through 50 strange discoveries is merely a prologue, as revolutionary instruments are now turning their gaze toward these cosmic clouds. The James Webb Space Telescope, with its colossal golden mirror, is an infrared marvel designed to see what optical light cannot. It will peer directly into the dense, dusty hearts of protoplanetary nebulae, watching as the first jets form and the initial chemical factories begin their work. We will no longer have to guess about the complex molecules hiding within these shrouds. We will be able to map them, identifying the specific polycyclic aromatic hydrocarbons and perhaps even more complex organics being forged in the chaos. This incredible sensitivity will likely solve the enduring mystery of the missing mass, revealing the vast, cold halos of neutral hydrogen and molecular gas that have eluded our detection for so long. We may finally see the true, full extent of a star's final gift to the galaxy, but with every solution comes new questions. What bizarre chemical pathways will we uncover in the frigid outskirts of a nebula? Will we witness the very moment a binary star system triggers its final sculpting outburst? The data flowing from these new observatories will not just provide answers, it will rewrite our textbooks, revealing phenomena we have not yet even dreamed of. The universe's most beautiful endings are still holding their deepest secrets, waiting for the right light to reveal.